Welcome back, Cesar. Today, I'm stepping into the role of your senior technical lead for a highly specialized briefing. Given your background in mathematics and software engineering, we're going to look at the foundations of chemistry through a lens you're already very familiar with. We are going to treat chemical reactions not as some kind of magic, but as a strict, zero-sum algebraic system. We'll be analyzing the precise architecture of chemical equations and seeing exactly how data integrity, which in this case is mass, is rigorously maintained. All right, let's dive right in.
So, here is the API documentation index for our session today. 1. The zero-sum system. 2. Equation technical specifications. 3. Iterative balancing algorithm. And 4. System state alignment.
Starting with Section 1, the zero-sum system and the foundations of stoichiometry.
To kick things off, we need to decode a bit of industry jargon, stoichiometry. It's derived from the Greek words for element and measure, so you can really just understand it simply as elemental measuring. It's the quantitative tool utilized for measuring the exact quantities of substances that are consumed and produced in any chemical reaction. You can picture it like the analytics dashboard that tracks literally every single byte of data flowing through our chemical process.
The underlying framework for all this elemental measuring was architected back in the late 1700s by a French nobleman and scientist named Antoine Lavoisier. He fundamentally shifted chemistry from just qualitative observation to rigorous, hard quantitative measurement. Basically, he is the original system admin of the chemical world, defining the unbreakable logic that governs how our physical environment operates.
Lavoisier famously stated, "Nothing is created, an equal quantity of matter exists both before and after the experiment." Put into our terms, this is the foundational axiom of the whole environment. Memory absolutely cannot be leaked, and matter cannot simply be deleted or fabricated out of thin air. The state of the system before execution has to perfectly match the state of the system after execution.
Formally, this axiom is known as the law of conservation of mass. In strict scientific reporting, it is stated that atoms are neither created nor destroyed during a chemical reaction. They are only rearranged. So, the exact same collection of atomic data is present before and after. At this chemical level, the universe operates as a perfectly closed zero-sum system.
Moving right along to Section 2, Equation Technical Specifications, where we define our inputs and outputs.
We can map our chemical architecture precisely like a data pipeline. On the left side of our equation, we have our reactants. These are our starting substances, essentially our system inputs. And on the right side of the equation, we have our products. These are the substances actually produced by the reaction, which serve as our system outputs. That reaction arrow right in the middle, it simply denotes the execution process itself, reading as produces or yields.
Now, clear communication of these specs is absolutely crucial in a professional setting. When a formula like the number 2, followed by H, a subscript 2, and O appears, it is read aloud as 2 molecules of water. You vocalize the physical reality of the data structure, not just the raw characters on the screen.
To ensure data integrity, we have to draw a really critical boundary between two types of numbers in our specifications. Subscripts, those are the small numbers tucked inside a chemical formula, are read-only constants. They define the chemical identity itself. If you alter a subscript, you change the molecule entirely. Water suddenly becomes hydrogen peroxide, which is a completely different substance. Coefficients, on the other hand, the large numbers placed in front of the formulas, are variable parameters. These are the parameters that are actively adjusted by us to align the system and make sure the inputs match the outputs.
Section 3, the iterative balancing algorithm. Let's actually compile a methane combustion.
Here is our standard operating procedure for this algorithm. When methane, CH4, burns in the presence of oxygen, O2, it produces carbon dioxide, CO2, and water vapor, H2O. To debug this system, we follow a strict chronological order. We start with the elements that appear in the fewest formulas. Step 1, balance carbon. Step 2, balance hydrogen. Step 3, balance oxygen. Okay, let's execute.
First, the input variables are identified in our system. We have our reactants, 1 molecule of methane, which is composed of 1 carbon atom and 4 hydrogen atoms, alongside 1 molecule of diatomic oxygen. So at this initial state, we have 1 carbon, 4 hydrogens, and 2 oxygens.
Subsequently, the outputs are analyzed for atomic parity. Our initial products are 1 molecule of carbon dioxide and 1 molecule of water. Now notice our carbon is aligned, 1 on the input, 1 on the output.
However, we've got an error in our hydrogen count. We input 4 hydrogens, but only output 2 in that water molecule. To resolve this, a parameter adjustment is required. A coefficient of 2 is placed in front of the H2O output. This gives us 4 hydrogens on the output side, so hydrogen is now balanced.
Finally, the system is aligned by addressing the oxygen count. With our previous adjustment, our output side now contains 4 oxygen atoms, 2 in the carbon dioxide and 2 in the 2 water molecules. But our input side only has 2. So we iteratively adjust the input coefficient, placing a 2 in front of the O2 reactant. And there we go. The debugging loop is successfully resolved. We have 1 carbon, 4 hydrogens, and 4 oxygens on both sides. The system is in a perfectly balanced state.
Section 4. System State Alignment. Let's do a quick remote stand-up summary.
To wrap up this sprint, here is our status report. Mass balance is perfectly ensured. Data integrity is fully verified across the entire chemical equation. Absolutely no data was lost. It was proven that atoms are merely rearranged via a passive, zero-sum process. And crucially, throughout our entire debugging loop, the subscripts were strictly maintained as read-only constants. We only ever manipulated the variable parameters, which are coefficients.
So, the big takeaway is that this strict mathematical framework governs all of chemistry. But I want to leave you with a final thought as we close this briefing, Cesar. Today, we basically assumed an infinite availability of our inputs. But if inputs are unbalanced in real-world memory limits, say we just run out of oxygen halfway through compilation, how exactly does the system handle limiting reactants? Think on that one, and we will compile that answer in our next technical briefing.